Alright, so what I wanted to do in this video is go over the parallel axis theorem because we didn't have time to do it in class today. So the idea of the parallel axis theorem, as I mentioned, is today we saw a number of expressions for the moment of inertia, and those expressions had the axis passing through the center of mass. An example of this is right here. This slender rod with the axis through its center, it's also passing through the center of mass. But what happens if we want to move the axis of rotation? So in part B, we're moving it to the edge of the rod. And so we've moved it so it stays parallel to the original axis, but it's not passing through the center of mass anymore. And so there is an expression for how we calculate the moment of inertia about some point P. So right here's our point P, and here notice this is through the center of mass. So what it's saying is if I want to find the moment of inertia about some axis that isn't through the center of mass, like point P, it's equal to the moment of inertia about the center of mass plus the mass of the object times the distance that I've moved the axis squared. And so that's called the parallel axis theorem. What we want to look at is how we get that expression. So here's a picture of an arbitrary object, and there are two important points on this object. Here is the center of mass, and notice we've placed it at the origin. And now here is point P. The idea being that we're going to move the axis of rotation to point P. And here is the mass, right here is the mass that we're looking at, where we're going to write, how would we write the moment of inertia of that mass? So we start off with some expressions. So if I wanted to find the moment of inertia about the center of mass, and so we would be measuring from the origin, it would be the sum of the mass, the m sub i's, times the radius squared. Well, the radius would be measured from the origin to where the mass is, and that would be like an r, like here. And that would be also given by x sub I squared plus y sub I squared, because that's the coordinate of that mass. That's where it is. And so that's the moment, how we would write the moment of inertia about the center of mass. Now, if I wanted to find the moment of inertia about point P, right here, notice that the distance away from m sub I here, from here, this would be this radius. And again, we can sort of use the Pythagorean theorem to figure out what that is, because the x distance would be x sub I minus a squared, and then this would be the y distance minus b squared. And just to keep in mind, the coordinate of point P is a, b, and that's where those values come from. So this is just really using the definition of the moment of inertia, is that it's the mass times r squared. Alright, so we're going to expand this because this has some quadratics in it. Alright, so we have all these terms here. Now, what I want to look at is some of these terms is this term and this term. And notice how they look a lot like the definition of the center of mass, the x and the y position. So for instance, the y center of mass will be given by m sub I y sub I over the sum of m sub I. And the definition of the center of mass in the x direction will be given as m sub I x sub I over the sum of m sub I. Now, and so you see those terms are here. But the way that we chose our coordinate system, the center of mass of both of these is 0, because we put the center of mass at the origin. That means that both m sub I y sub I and m sub I x sub I are equal to 0. So those terms actually cancel out, or, well, they don't cancel out, they're just 0. And so our IP now is the sum of m sub I x sub I squared plus the sum of m sub I a squared plus the sum of m sub I y sub I squared plus sum of m sub I b squared. Now let's go back up and look at this definition right here, because we actually do have those terms. We have this term and this term. Those are, so if we put them together, we have m sub I x sub I squared plus y sub I squared. And then we can also put the other terms together, sum of m sub I a squared plus b squared. So we're going to go back to the next page. So what we have so far is I sub p is m sub I x sub I squared plus y sub I squared, and then the sum of m sub I a squared plus b squared. That's where we got so far. Well, this term right here is just the moment of inertia about the center of mass. We had written that at the very beginning. And a squared plus b squared, if we look at our picture, is just equal to d squared. So we've actually gotten to the parallel axis theorem. And that's just big M, and so it's the center of mass plus big M d squared. And that is how you get the parallel axis theorem.